All right, everybody else has been called. Let's see if they get here. And we're gonna get started. So, good afternoon. I hope y'all's day has been going all right. That classes didn't go too fast for you. Maybe you got the opportunity to sleep in because classes didn't start till like 12:40. Maybe you didn't. Maybe you're able to use this extra time in the morning to get caught up on things or just enjoy a cup of coffee. Either way, I hope your day's going well. This class is going to be fast, so to say. I'm going to do a review going back all the way to chapter 4, the very first chapter we covered in this class. It's going to be kind of like drinking out of a fire hose. I don't suggest trying to write all this stuff down. It's going to be coming too fast. This PowerPoint presentation is already loaded into Canvas in the Things You Might Need module. So you will have access to this. It's also going to be linked in today's calendar date in Canvas on that front page there. All right. So you will have access to it. The amount of time we have in class today is not going to be enough time for me to get through absolutely all of this presentation. I'll get through as much as I can. But we're starting back at chapter 4. We're going to work our way up to as close to chapter 10 as we can get to. But everything from chapter 4, chapter 1, chapter 2, chapter 5, 6, 7, 8, 9, and 10 is a part of this presentation. It will not cover absolutely everything from those chapters because that would be a much longer presentation. But it's going to cover the main points as far as I'm concerned. Right? So we're going to get this shindig going. If you have questions along the way, you need me to clarify something, please stop me and tell me. But again, as far as notes is concerned, I recommend if there's something that you completely forgot and you want to make sure you remember it, you want to jot that down, that's fine. Don't try to write it all down. There won't be enough time to write it down. But you will be able to look back at it if you want to take other notes. So, let's see if we can make this work. Alrighty, so a time to review what we have seen so far. And we've covered the following chapters. Chapter 4, Sampling and Surveys and Experiments. Chapter 1, How to Describe and Display Categorical Data and Quantitative Data. Chapter 2, Percentiles, Mean, Median, Range, IQR, Standard Deviation, Density Curves, and the Normal Distribution. Chapter 5, yes, that is correct. We skipped chapter 3. It's coming back at the end. Sorry. Chapter 5 is probability, simulations, conditional probability, and independence. Chapter 6, discrete and continuous random variables. This is the beginning of semester 2. Transforming and combining random variables, binomial random variables, and geometric random variables. Chapter 7 covered sampling distributions of sample proportions and sample means. Chapter 8 covered confidence intervals for estimating population proportions and population means. Chapter 9 covered significance tests for testing claims about population proportions and population means. Chapter 10 was comparing two populations or groups through confidence intervals and significance tests. All the things we've seen so far as the main topics and chapters. In chapter 4 about designing studies, we first talked about sampling and surveys. We want to know how to sample. We can do a convenience sample, voluntary response sample. Those usually result in some form of bias. We have a random sampling, which is much more advisable, starting with our simple random sample, which we lovingly refer to as the SRS, and we have our stratified random sample, cluster sample. We always want to be concerned about undercoverage, non-response, and possible response biases. For example, wording of a question or the person you have asking the question. Those could all result in some form of bias. We also need to learn how to, we learned how to conduct experiments. All right, there's observational studies and there are experiments. Observational studies is simply sitting back and observing something that happens and writing down what happened. Right? An experiment is when you purposefully impose some sort of treatment onto an individual or a group of individuals. Right? We have treatments, which are the things that you're doing to your individuals. Experimental units, which is the smallest unit of individuals that can receive a treatment. And then we have our subjects. Subjects are the people or things or animals or whatever that are participating in the study or experiment. To experiment well, we need to make sure we're using random assignment, comparison, control, and replication. We need something to compare to. We want to randomly assign who gets what treatment so that it's unbiased as best as we can. We need to have control, meaning we want to control the variables. Control does not mean have a control group necessarily. You can, gives you something else to compare to, but in this sense, control is saying, how am I going to control other variables that could affect my outcome? Right? One example of control is making sure that everyone's receiving their medication at the same time. Right? That they're all getting a similar diet. Things like that, those have control over other variables. And we also want replication. We need to do enough of this thing to feel justified that our results are good. We need to be completely randomized in our design. We need to be aware of placebo effect, whether or not we want to use a double-blind, single-blind study, and then ultimately we want to know if our results are statistically significant, which we can now determine. We will use a block and randomized block design at times, and also matched pairs design is a special type of randomized block design. Matched pairs design results in one sample T procedures, which we learned about at the end of chapter 9. Lastly, we have a scope of inference, which is what we can actually say our results are about. Right? Can I conclude something about the larger population in general, or can I only make a statement about the people who participated in my study, or people similar to those? What is my scope of inference? Here's a quick little graphic here about the different types of sampling. We have our simple or random sample, which is, assign everybody a number from a random number generator and then select 5 numbers. Boom, simple random sample. Put everyone's name in a hat and randomly draw 5 people's names. Simple random sample. We have our stratified random sample, and that's where you group people based on similar characteristics, and then randomly select people from each of those strata. The cluster sample is when you group people based on proximity. They're just close together, so we're going to group them together. And then I'm going to randomly select clusters to participate in my study, meaning everyone in the cluster is participating if the cluster is selected. People whose cluster is not selected are not part of the sample. Right. For our completely randomized design, we start by randomly assigning, in this case, students to 2 groups. We evenly distribute them between the 2 groups, 30 and 1, 30 and 2, and then we randomly decide who or which group will get treatment A and which group will get treatment B. We could do this by flipping a coin. And then we compare the results. That is a completely randomized design. We randomly selected who goes in which group, and then we randomly assign the treatment. In a block design, we group the students based on something. It could be grade level, right? 9th graders and 10th graders. And then we randomly assign them to 2 groups within each group, each block, and then randomly assign the treatment within each of those groups within each block, and then compare the results of those 2 blocks. And then our special case of a block design is our matched pairs design, where we have an individual or a pair of individuals who are similar that create each of the blocks, and then we randomly assign one of 2 treatments to the pairs of individuals, or randomly have one individual have both treatments at different times, and then compare the results. We then are typically interested in the difference. Did one thing have a bigger impact than the other? And then that difference number becomes the single statistic that we're concerned about, which is why we use 1 sample T procedures. Now that we know how to design studies, we move into chapter 1 of exploring data. All right, we want to make sense of our data. We have individuals and we have variables. Right? Variables represent things about the individuals that we're concerned about and we want to know about. Right? Categorical variables, we have categorical variables and quantitative variables, and then we have distributions of those things that help us see what they are. Right? As the name implies, categorical variables have to do with categories, right? Left-handedness or right-handedness, right? Brown eyes or blue eyes or gray eyes, right? These are categories. Right? They're not values. Right? I can sometimes count the number of things in a category. However, it wouldn't make sense for me to average the color of someone's eyes. Quantitative variables, on the other hand, make sense to calculate an average of. Right? Height would be quantitative. It's a value. Weight would be a quantitative variable. Right? Scores on a test. Right? We can also create categories from those values. Right? That's a whole other thing, but we can do it. Right? Categorical data we can represent with bar graphs and pie charts and two-way tables. We can have marginal distributions and conditional distributions, and that can help us determine association. Quantitative data, we will use dot plots, histograms, stem plots, back-to-back stem plots, split stem plots to then display our data, which can help us see the shape and determine the center and spread and possible outliers of that data. We cannot do any of those things with categorical data. Categorical data does not have a shape because we can move the categories around on the x-axis and then it changes. Right? Which also means it doesn't have a center because, again, I can move around those things. It doesn't have a spread, and there aren't possible outliers in categorical data. So none of these things apply to categorical data, only quantitative. And we can use the acronym SOX or CUSP to remember that we have shape, center, spread, and outliers. Our distributions of quantitative data can be symmetric or skewed. Right? If it's skewed, it can be skewed to the right if the tail is on the right, or skewed to the left if the tail is on the left. Symmetric could mean that it's unimodal or bimodal or multimodal, or any of those distributions could be any of those things. And a special case of a symmetric distribution is our normal distribution. When we're describing quantitative data, we have the center, which can be described with the mean or median. It makes more sense to use the mean if it's symmetric and median if it's skewed. And again, we want to have the spread. The range is the most spread measure of spread. It's the maximum minus the minimum. Interquartile range goes along with the median, where it's the distance between Q1 and Q3. And then standard deviation, which goes along with our mean and a symmetric distribution. We want to be able to identify outliers, and this is most easily done using the 1.5 times IQR rule, which is multiplying 1.5 times the value of the interquartile range, and then adding it to Q3 and subtracting it from Q1. Anything outside of those ranges, the upper and lower bound, are then considered outliers. We can see this easier by using the 5-number summary and a box plot, which has the box in the middle, which is the IQR, and the minimum and maximum on either side. Anything, that goes beyond our 1.5 times IQR on that, easy to see. We can see those things. We can compare distributions. This is what categorical data can look like in a pie chart and a bar graph. Notice there is space between the bars in a bar graph. Here's a two-way table showing two different sets of categories and their intersections and the marginal distributions. And then we can display our quantitative data with a box plot, a histogram, a stem and leaf plot, or a dot plot, which are represented here on this little picture. Right? One thing I want to point out, if you look at the histogram and the bar graph that are on this page, the histogram has bars that are touching. It's because they're supposed to. Bars on a histogram should touch. Where one bin ends, the next one begins. There is no space between bars in a histogram. Right? The only time you end up with space between bars is if there is no value in a certain bin. Because I can't just go like 1 to 5, 5 to 10, then because there's nothing in 10 to 15, I can't just not list that one. It has to be listed. Okay, so if that bin is empty, I don't draw a bar there, and then the next bin, there's no more stuff, I have another bar. But these are continuous. One bar ends, the next bar begins. Modeling distributions of data, Chapter 2. We want to be able to describe location in a distribution, which can be done with percentiles, cumulative relative frequency, and standardized scores, or z-scores, which is a form of transforming our data. Right? When we standardize a score from an original value to a z-score, we have transformed that data point. When we have that transformation, we use density curves and normal distributions to learn about the data. Right? A density curve has an area of 1 under the curve, and then the mean and median are specifically related under a density curve. All right? If the distribution is skewed to the right, the mean will get pulled to the right. It will be to the right of the median. Right? If the density curve is skewed to the left, the mean will fall to the left of the median and get pulled in the direction of the skew. Right? We have a normal distribution, which is notated with n parentheses mu comma sigma, where mu is the mean and sigma is the standard deviation, and those two values will completely describe a normal curve. The 68, 95, 99, 7 rule applies to our normal distribution, meaning that 68% of our data is between 1 standard deviation of the mean, 95% is between 2, and 99.7% is between 3 standard deviations of the mean. We have the standard normal curve, which then is in terms of like z values, 0, 1, 2, or 3, or negative 1, 2, or 3. We use table A along with these standardized scores in the standard normal curve to determine probabilities and make comparisons with z-scores. Normal distribution calculations. We can use this normal distribution, table A, and standardized scores to find the proportion of a curve, proportion under a curve based on a given value, or we can find a value based on a given percentage of proportion under the curve, percentile. We can work forward or backwards through standardizing and p-value essentially, or go from p-value back to standardized back to the original. We can also assess normality, which comes in handy when we're doing confidence intervals and significance tests. We want our distribution to be approximately symmetric and bell-shaped, close to the 68, 95, 99, 7 rule. And we can also use a probability plot, which is something your calculator does, to assess normality. If we get a straight line from a probability plot, that thing is normal. If we do not, there's a possibility it's skewed. Here's a little graphic of our 68, 95, 99, 7 rule. And then the formula to standardize a score, where we have our score minus the mean divided by the standard deviation. That brings us to chapter 5, which is about probability. We have randomness, probability, and simulation. Probability is always between 0 and 1 and describes the proportion of time a random outcome would occur in the long run. Simulations can allow us to model long-run behavior and imitate chance behavior without actually having to do all the trials. We have specific probability rules. All right. We have a sample space as a set of all possible outcomes. I'll use the example of rolling 2 dice and having the outcome be the sum of the 2 dice. When rolling 2 dice, there are 36 possible combinations, which means there's 36 possible outcomes. The probability model consists of a sample space and probability for each outcome. Right? An event is any collection of outcomes from some chance process in a subset of the sample space. Okay, so our probability model for rolling 2 dice consists of 36 possible outcomes. Each outcome is the value of 1 die and the value of the other die. Right? There's 36 possibilities. Probability of each of these outcomes is 1 out of 36. They have an equal probability, right, of each individual combination. If I collect these things, there's a specific event. If I want to say I want event A to be the event where the sum of the 2 dice is 6 or less, I would then look at all the combinations of the 2 dice that result in a sum of 6 or less. Okay. If all outcomes in the sample space are equally likely, the probability of event A occurs as P of A equaling the total number of outcomes in event A, total number of different combinations of the 2 dice that result in 6 or less, divided by the total number of outcomes, in this case 36. Right. 2 events are mutually exclusive if they have no outcomes in common. They are disjoint or mutually exclusive. This could be an example of if event A is the sum of the 2 dice are 6 or less, and event B is the sum of the 2 dice is 10 or more. I can't have both those things happen at the same time. The dice cannot simultaneously be 6 or less and 10 or more. So those two events are mutually exclusive. They cannot happen at the same time. We have our complement rule. This is the probability of A complement is equal to 1 minus the probability of A. If event A, again, is the sum of two dice being 6 or less, the complement of event A is the sum of two dice being more than 6. The probability of A complement is 1 minus the probability of event A. Sometimes it's easier to calculate the complement than it is to calculate the actual event. Right? It just depends on how things are defined. All right. Our addition rule for mutually exclusive events is the probability of A union B is equal to the probability of A plus probability of B. Remember that union is or, meaning what's the probability that the dice have a sum 6 or less, or we get a pair of dice that have a sum of 10 or more, right? That is an or thing, meaning I could have either of those things happen and I'm okay. They don't have to happen at the same time. Two-way tables and the general addition rule. When finding probabilities involving two events, a two-way table can display the sample space, making probability calculations easier. We saw an example of a two-way table earlier on a previous screen. It allows us to see the count of each thing happening related to all of the possible categories. Right? We have our general addition rule for two events. If A and B are any two events, meaning they don't necessarily have to be mutually exclusive, any two events resulting from some chance process, and the probability of A union B is equal to the probability of A plus the probability of B minus the intersection of those two events. Right? The probability of both things happening at the same time. Now, when the events are mutually exclusive, the probability of those things happening at the same time is 0, which is why we get the first rule that's on this page, or the first addition rule on this page. This next one accounts for the conditions when they're not mutually exclusive. We have to subtract the intersection, so we don't count it twice. Venn diagrams can also help determine probabilities by modeling the sample space of a chance process involving two events. Remember, our Venn diagram is like when you have two circles that intersect, you have that little sliver in the middle that they're shared, right? That can help us kind of count events and things and have another visual representation. We also have conditional probability and independence. The notation P of B given A, right? The up and down line there between B and A is given. Right, represents the probability that event B occurs given that event A has occurred already. And we can also say P of A given B. Right? Probability of A given B is equal to the probability of A and B divided by the probability of B. Right? The probability of B given A is equal to the probability of A and B divided by the probability of A. All right, so in this scenario here, the numerator will always be the intersection of the two events listed here. And the probability of A and B is the same as the probability of B and A, so it doesn't matter which way I write these. The denominator, probability of B here, is whatever is in the second spot here. What was the given event? In this case, the given event is B, so we do the probability of B on the denominator. If it's probability of B given A, then the denominator is probability of A, because A was the given event. And this is, I don't know why PowerPoint does not like this slide. It keeps stalling on this one. Conditional probability and independence. Right, we have our general multiplication rule, which says the probability of the intersection of A and B, right, probability of event A and event B happening at the same time, is the probability of A times the probability of B given A. Okay. We can also find this as the probability of A and B is equal to the probability of B times the probability of A given B. Works that way too. When chance behavior involves a sequence of outcomes, a tree diagram can be used to describe the sample space. This is when we have like that branching of probabilities happening. Right? We saw some examples of this earlier in the year. It could be, the probability of flipping a coin, right? Flipping a coin once and you get a heads, and then flipping it again and you get another heads, and flipping it again, you get another heads. Each time you flip the coin, there's two possible outcomes, heads or tails. Right? And let's say we have a non-fair coin, so the probability of a head is maybe 60%, and the probability of a tail is 40%. We get a heads, and then another heads, and another heads, and another heads. It goes along this series of events. What's the probability of getting 4 heads in a row? We would use a tree diagram to kind of help see how that works. It can be a visual representation again. When knowing that one event occurred does not change the probability that another event occurs, we say the two events are independent. All right. When two events are independent, the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. Right? Because the fact that B happened doesn't matter, or the fact that A happened doesn't matter, right? Because A and B are independent. If two events are mutually exclusive, meaning they're disjoint, they cannot be independent. Right? And this is because if two events are disjoint and I know one happened, I know 100% that the other one did not happen, which meaning it definitely had an effect on whether or not the next thing happens. Right? If events A and B are independent, then the probability of A and B is the probability of A times the probability of B. All right. And again, this pairs up with the very first thing on the very first rule on this page, the general multiplication rule, except these are independent events, so the probability of B given A is equal to the probability of B. And we get what's at the bottom. That gets us to chapter 6, random variables. Give it a second. There it is. Discrete and continuous random variables. A random variable takes numerical values determined by the outcome of a chance process. All right. So again, we can use our rolling of 2 dice as an example. The probability distribution of a random variable x tells the possible values of x and the chances that each of those values occur. We could have x represent the sum of 2 dice being rolled, 2 fair 6-sided dice. X can have the values, can take on the value 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. The probability of each of those sums occurring is different, right? There's only one way to have a sum of 2. On those dice, we get 2 1s, so 1 out of 36, right? There's 2 different ways to get a sum of 3. We can roll a 2 and a 1 or a 1 and a 2, so we have 2 out of 36, and so on. So the probability of each of the random variable x taking on each of those values is different based on that sample space. Discrete random variables have a fixed set of possible outcomes. So in the example, the random variable x is discrete. There are only those possible outcomes 2 through 12. Continuous random variables take all the values in some interval of numbers. And when they say all the values, that means all the values. Right? I could have the interval 0 to 1. All right? If the variable is continuous, it can take any number between 0 and 1, meaning it could be 0.1, 0.11, 0.23, 0.56, 0.5, 0.111111. Those are all different values. All right? Continuous variables have an infinite number of possibilities. If x is a random variable, the mean or expected value of the average of the values of x is mu sub x equaling the expected value of x, which is equal to the sum of each outcome times the probability of that outcome. And that's shown here in this formula. The first outcome times probability of outcome 1 plus the second outcome times probability of outcome 2, and so on. Okay. We have variance of a random variable. X is the variance of x is equal to the sum of the difference between the outcome and the mean squared times the probability of that outcome. I think I messed this. I don't think I need an I on that mu. I think I messed it up. And then we have the standard deviation of a random variable x, and that is the square root of the variance. We can transform and combine random variables. Right? If we add or subtract a constant to a random variable, this will increase or decrease measures of center and location. which is mean, median, or percentiles. It will have no effect on shape or spread. Multiplying or dividing a random variable by a constant multiplies or divides measures of center, location, and spread, which meaning it will affect mean, median, percentiles, IQR, range, and standard deviation. But again, has no effect on shape. This is why when you do like a sampling distribution and the parent population is known to be normal, the sampling distribution will also be normal because the transformations that are happening doesn't change the shape. And we use these things in chapter 10 here, transforming and combining random variables. If x and y are two random variables, then the mean of the sum of x and y, random variables, is equal to the mean of x plus the mean of y. And the difference, the mean of the difference between x minus y, is equal to mu x minus mu y, or the mean of x minus the mean of y. If x and y are independent random variables, then the variance of the sum of the random variables is the variance of x plus the variance of y, and the variance of the difference is also equal to the sum of the variance of x plus the variance of y. And again, we use these difference things right here on the end in chapter 10. We also have binomial and geometric random variables. For a binomial random variable, we need to have a binomial setting. This means that we need to check our bins, meaning the random variable must be binary. It can either be a success or a failure. Independent, meaning that knowing what happened in one trial has no effect on the next trial. There needs to be a specific number of trials, right? And the probability of success in each trial has to be the same. If x has a binomial distribution with parameters n and p, where n is the number of trials, sample size, and p is the probability of success, the possible values of x are the whole numbers 0, 1, 2, up through n. You can only have as many successes as the number of trials we have. The binomial probability of observing k successes in n trials is p of x equaling k is equal to n choose k. That's what's in parentheses there. It is not a fraction. There is no division bar. N choose k is a mathematical thing that calculates how many different ways can I have k successes or k things chosen out of n trials. And your calculator can do this. And it's based on the binomial coefficient, right, which is in our notes, but your calculator does this. Times probability, or times p to the power of k, where p is the probability of success, k is the number of successes, times 1 minus p, or the probability of failure, times, or to the power of n minus k, which is the number of failures. Right, the mean and standard deviation of a binomial random variable x are mu sub x equaling np, and sigma sub x equaling the square root of np times 1 minus p. To have a geometric random variable, we need to have a geometric setting, which means we have repeated trials of the same chance process in which the probability p of success is the same on each trial, meaning these events are independent, these trials are independent. But the goal is to count the number of trials it takes to get a single success. So we will always only have one success in a geometric setting. That's the big thing that sets it apart from a binomial setting. If y has a geometric distribution with probability of success p, the possible values of y are the positive integers 1, 2, 3, up to infinity, essentially, because it could take a really long time to get our first success. We don't know. The geometric probability that y takes any values is p of y equaling k equals 1 minus p times k minus 1, or not times, to the power of k minus 1 times p. And that is essentially the probability of failure to the power of the number of failures times the probability of success. And the probability of success p is essentially to the power of 1 because we only have one success. The mean of a geometric random variable is mu sub y equaling 1 over p. That gets us to sampling distributions. Chapter 7. Right, a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. The sampling distribution of a sample proportion is summed up in the following. If we choose an SRS with size n from a population of size capital N with proportion p of success, we then let p hat be the sample proportion of successes. Then the mean of the sampling distribution of the sample proportion is equal to p. Right? And then the standard deviation of the sampling distribution of the sample proportion is equal to the square root of p times 1 minus p divided by n. These results are only valid and usable if the 10% condition and large counts conditions are met. The 10% condition makes the standard deviation valid, and the large counts condition allows us to use the mean and standard deviation in a normal distribution and normal calculations, which means we use table A. We can also have sampling distributions of sample means. Right? And suppose that x bar is the mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of the sample mean is equal to mu, and the standard deviation of the sampling distribution of the sample mean is equal to sigma divided by the square root of n. The standard deviation is valid if the 10% condition is met, and we can only use normal distribution calculations if the normal large sample conditions are met. Right? And this chapter is referred to as the central limit theorem, saying that if the sample came from a population that was normally distributed, then we're okay. Or if the sample size is sufficiently large, equal to or greater than 30, we can also assume normality and use the normal distribution. And then we get chapter 8, confidence intervals. When we interpret a confidence intervals and confidence levels, if you're interpreting a C% confidence interval for an unknown parameter, we want to say we are C% confident that the interval from some number to another number captures the true, whatever it is in context, the true population proportion of students who tie their shoes. I don't know. Right? And then when we're interpreting the confidence level, all right, to say we're C% confident is shorthand for if we take many samples of the same size from this population, about C% of them will result in an interval that captures the actual parameter value. Meaning there is a possibility that some proportion will not result in an interval that works, so to say. Depends on the confidence level. When we're calculating a confidence interval, right, the confidence interval for estimating a population parameter, population proportion or population mean, has the form statistic plus or minus critical value times the standard deviation of the statistic. I'm sorry that went off center. And the margin of error is the critical value times the standard deviation of the statistic, right? Everything to the right of the plus or minus sign, right? The margin of error essentially builds the interval. Estimating a population proportion. Before constructing a confidence interval, you must check the random 10% when sampling without replacement, and large counts conditions are all met. Then use the one sample z interval for a population proportion inference method, which is p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n, where z star is the critical value for that standard normal curve with c% of its area between negative z star and z star. So again, we use table A along with knowing whatever the percent confidence interval is we're looking for, right? Determine what proportion of that percent is on each tail, using one of those, right? And determine the z star value. Okay, it's usually going to be a negative number. We use the positive version in the formula here. Don't forget to use your 4-step process. This goes along with confidence intervals and significance tests, and it'll come up again in the next chapter we're doing. Right? State, plan, do, conclude. 4-step process. Do it again. Right? To determine the necessary sample size for a given C% confidence interval with a maximum margin of error, ME, solve the following inequality for n. In this case, because this is confidence intervals for a proportion, the margin of error will be a percentage which you convert to a decimal. Right? It is the maximum acceptable margin of error, which is why we have the inequality. Use the z star that corresponds with whatever the percent confidence interval you're interested in from table A is, and p hat is your sample proportion. N is what we don't know. We do not have a value for n. Leave it as n. In this calculation, solve for n. If you put a value there, you're not actually solving. You have numbers everywhere. You're not actually solving for anything. You're just moving numbers. Estimating a population mean. Before constructing confidence interval, you must check the random 10% when sampling without replacement and normal large sample conditions are all met. Then use the one sample t interval for population mean inference method, which is x bar plus or minus t star times s sub x divided by n square root of n. Right, the s sub x divided by square root of n is the standard error, where t star is the critical value for the t to the n minus 1 distribution, which the n minus 1 refers to our degree of freedom, which is 1 less than the sample size, with c% of its area between negative t star and t star. Lastly, well, almost lastly, do your 4-step process. To determine the necessary sample size for a c% confidence interval with a maximum margin of error of ME, solve the following inequality for n. The major mistake that I saw on the self-assessment and free response question is that you used a percentage, and that would be incorrect. If the maximum margin of error is to be within 1 unit of something, then ME is 1, not 0.1, not 0.01. It's not a percent. It's just 1. And again, in this case, we use z star. So again, we're referring to table A to determine the sample size. Because again, if we don't have a sample size, we don't have a degree of freedom. So we have to use what we have, which is table A, which doesn't need a degree of freedom. We're going to stop here. So there is still chapter 9 and chapter 10 stuff here. Obviously, we're not getting there today. I do highly recommend that you look at the last bit of this in Canvas to see the review for chapters 9 and chapter 10, if that is something you're interested in. Tomorrow we will be doing the practice AP demo thing within the AP testing app. If you don't have access to that, I'll have an alternative thing for you to do. And then next week we'll be starting our last unit, which is a combination of the last few chapters. So if you have any other questions, comments, or concerns, please let me know. And I will see you tomorrow, same time.